Hi, this is Tong, and today we're talking about the railgun. A railgun is basically a big circuit composed of two rails, one positive and one negative, attached to a power source. A conductive armature carrying the projectile lies between them, completing the circuit. When the rails are powered by an electromagnetic pulse, the armature guides the projectile out of the muzzle. So what causes the armature to move forwards? When the rails are powered, a magnetic field forms around the rails and armature, which act like wires. Because of the direction of the current and the magnetic field, a Lorentz force acts on the armature. Since we know that the direction of the current goes like this, we can use the right-hand rule to determine the direction of the magnetic field, like this. We can see that in between the rails, the direction of the magnetic field is upwards. Thus, we can use Fleming's right-hand rule to determine the direction of the force on the armature, like this, which is away from the power source or out towards the muzzle. As the armature leaves the muzzle, the circuit's broken. To figure out the magnitude of the force, we can use the equation for Lorentz force, which is simplified to F equals ILB, where I represents the current in amperes, L represents the length of the rails in meters, and B represents the magnetic field strength in teslas. Since the purpose of the railgun is destruction, we want to maximize the momentum and kinetic energy, given in the two equations. Since there are limits on the mass of the projectile, this is done by increasing the velocity. Applying one of our kinematic equations, the projectile starts from rest, so to increase the muzzle velocity, we must either increase the distance, which is rather unrealistic, or the acceleration, which is done by increasing the force, as decreasing the mass decreases the momentum and kinetic energy. As you can see, there are three factors here. The magnetic field strength is dependent on the material itself and its properties, so it starts to increase. And the length, which is equal to the distance, as before, is difficult because of the cost, size, and weight of very long rails. Therefore, railguns require an incredibly high current, around 5 megaamps, which gives the projectile a muzzle velocity of 2,000 to 3,500 meters per second and a muzzle energy of 5 to 50 megajoules. This large range is due to the differences in engineering. You may be surprised to learn that the idea of railguns was first proposed way back in 1918 by French inventor Louis-Octave Fauchon-Villebly, who patented his design as patent number 1,421,435, electric apparatus for propelling projectiles. Its basic structure was very similar to the modern design, except instead of an armature, the projectile had wings that allowed it to glide on the metal buzz bars. The first working, though extremely weak, railgun was built during World War II by Joachim Honster of the German Ordnance Office. In 1944, the Luftwaffe Flak Command commissioned railguns with muzzle velocity of 2,000 meters per second to be used as anti-aircraft weapons. However, they were never built, and the 1947 report found that each gun would require enough power to illuminate half Chicago. The power necessary was finally provided when Sir Mark Oliphant finished building the world's largest 500 megajoule homopolar generator in 1963, which was used to power an experimental railgun. As of 2020, the American Office of Naval Research was exploring ways to efficiently power the railgun, mount it on warships, and increase the rate of fire. Ultimately, at the end of 2021, the US decided to pause development on the project because of the increasing cost of the already $500 million project, combined with the maturity of other weapons and the inviolability of the railgun. The two greatest challenges facing the development of railguns are the power and material requirements. The power source must be able to sustain a tremendous current, especially to fire multiple shots in quick succession. Modern railguns are usually powered by capacitors and compensated pulse alternators, or compulsators, as they can store a great amount of energy. However, this has an extremely sluggish rate of fire, as they have to be slowly charged by other power sources just for a single shot. As for the materials, the projectile and rails must be able to withstand the extreme heat generated by friction and electricity when the railgun is fired. In addition, the rails must be able to endure the repeated recoil and violent forces from each shot, while also being conductive. Currently, railguns have not had many impacts on the world, as there are only prototypes. However, an indirect impact can be seen in the innovations in power sources it has helped drive, as well as its contribution to strained foreign relations as a destructive weapon. Its extraordinary theoretical impacts lie in its superior muzzle velocity compared to conventional shells. Firstly, it has much greater destructive force, which makes the explosives that normal shells carry obsolete. This means smaller projectiles, which are easier to load and store, as well as eliminating the risk of storing explosives in the combat environment. Other theoretical applications include the launching and assisted launching of spacecraft. The biggest challenge facing this is the acceleration required to achieve escape velocity over the distance of a feasible railgun barrel is too great for humans to withstand. However, they could be used to launch unmanned spacecraft, and other rail designs like the Helix, which should increase the distance and thus decrease the acceleration needed, are actively being considered. So, is the railgun a promising new technology, or just talk? Alas, though it has many promising theoretical applications, the power and material requirements mean that we are unlikely to see an applied railgun in the near future. Thank you for listening, and here are my references.